sunrise tomorrow, inspire the world to follow.
Okay, I am Shumanto Kundu, Assistant Professor of Department of Electrical Engineering, Narlo Institute of Technology under GIS Group Educational Initiative. So today we will start module 2 on the course of E701 electric drive, and in module 2 we will deal with selection of motor power rating. Okay, so we will start our lecture number 5. Before we proceed into the details, theoretical or mathematical or analytical details of selection of motor power rating, we should understood what is our objective of this module or today's class. So this is my objective, to become familiar with motor power rating, and the CO which it will covering is student will be able to select electric motor for a particular drive based on characteristics. Okay, so let's start selection of motor power rating. Okay, so we should know that the power rating of motor of a specified application must be carefully chosen. So when we are choosing the motor for a particular application, whether it can be a domestic application or it can be an industrial application, we should choose very carefully, because to achieve the economy with reliability. Now when you are using a motor for a particular application, if it happens that motor has insufficient rating, then what will happen? It fails to drive the load, so which is the prime motto of the motor, and the second, it will lower the productivity and the reliability through frequent damages and shutdown due to overloading of the motor and power modulator. So there are two possibilities: one, it fails to drive the motor; second, if it is possible to drive the load, but its productivity will reduce and it will go through frequent damage, and due to overloading of the motor and power modulator, it will shut down. Now what will happen if we use motor with higher rating, with having which have extra power than what we exactly needed for that particular application? Then first of all, the initial cost is high, because if I require a 10 horsepower motor, and for that purpose if we use a 100 horsepower motor, then the cost will increase. Also extra loss of energy, so it is uneconomical, and especially for induction motor and synchronous motor, it will operate below the rated power factor. So if it's operate below the rated power factor, so somehow the efficiency will also be affected. So we cannot compromise with power factor and efficiency. So when we are choosing a motor for a particular application, its rating cannot be insufficient or it cannot be extra, it cannot be surplus rating. Okay, so in both cases it is a problem. So now it is clear that heat is produced due to losses in the copper, iron and friction during motor operation. When we have studied our basic electrical machine, we have know that heat is generated due to the machine losses, I square R loss and iron and friction losses. This is basic physics, basic concept of machine, we all know. Now, as the temperature of motor increases due to this heat generation, so after certain time it will cross the ambient value. Okay, so now what happen, it will cross the ambient value, so it will try to dissipate its extra heat to the surrounding medium. As a result, so when the outflow of heat increases, so the more the temperature rise, the more outflow of heat will happens. Equilibrium sets. When the equilibrium will sets, now when the heat generated becomes equal to the heat dissipated. Now, what these things you should very clear, the amount of outflow of heat is basically what? It is a function of temperature rise of the motor. It is a function of temperature rise of the motor. So, if it is a function of temperature rise of the motor, so as the motor temperature rise, heat outflow increases, and if the heat outflow increases, so it will disturb the equilibrium. So, equilibrium only sets when the heat is generating by the motor beyond the ambient temperature will be equal to the heat dissipated, that is motor temperature has to reach a steady state value. The motor temperature reaches steady state value when this equilibrium occur, and it depends on power loss. So, if the power loss is less, it will reach the steady state very easily, or if the power loss is higher, it will take some time, and the power loss again depends on the output of the machine. So, this dependence of the temperature rise on output power is basically known as thermal loading of the motor. So, basically what is the conclusion of this thermal loading of the motor? The machine, when machine in running condition, due to losses in the machine, its temperature start rising and it crosses its ambient temperature, and when it crosses the ambient temperature, it will start dissipating its heat to the surrounding medium, and equilibrium sets when the heat generated will become the heat dissipated. That is, the motor will reach the steady state depending on the power loss. So, power loss is directly affecting the steady state condition, and again power loss is directly proportional to the output power. More the output power, more the power loss. Okay. So, this is basically thermal loading of the machine. Now, steady state temperature is not same in all parts of the motor. Okay, it is highest in the winding. Why? Because its low density conductor is high in the winding, because loss density in the conductor is high, and the dissipation rate is also low, because the winding are embedded through insulator in a slots. So, it cannot able to come directly into the exposure of the cooling air. So, as because it is not directly exposed to the cooling air and it's wrapped in insulating material with partly embedded in slots, so the temperature of this winding part is higher than the other part. And another important thing is, when we are producing or when we are building the motor, the various material are used in the machine. Heterogeneous, the motor is basically a combination of heterogeneous material, it's not combination of a homogeneous material, because we have seen our in basic electrical machine that core is made of certain material, winding is made of copper, frame is made of some other thing, brushes are made of some other thing. So all these things are different. So among all these things, the insulation has the lowest temperature rise. The insulation has the lowest temperature limit, and depending on the temperature limit, insulating material employed in the electrical machine are divided into certain categories. Again, we have learned this in our basic electrical machine. So this is the chart of the insulation temperature limits. Okay, so my motto is to keep the insulation material lowest temperature limit. Okay, now suppose for a specific operation, motor rating should be choose such that the insulation temperature never exceeds the prescribed limit. So what will happen if it happens? Suppose the insulation temperature is higher than what is particularly required that particular operation, so it will immediately lead to the thermal breakdown, and which leads to the short circuit, and it will damage the winding. Okay, so motor rating should be chosen such that for a particular operation, that insulation temperature never exceeds the prescribed limit. Okay, so if it's exceeds prescribed limits, so there will be a thermal breakdown, causes short circuit, and which leads to the damage. Now if we operate a constant power and speed load, then determination of motor power rating is simple. But in reality, most of the loads are variable power and speed, and the pattern of this variation are different for different applications. So if you are deciding paper mill, so it will be different with the our traction drive. So for different application, it has different pattern. Okay, now thermal model. So if different application has different pattern, so what is my objective? My objective is to obtain a standard thermal model for the machine, which can be used to calculate the motor rating for various classes of motor duty. And what are the various classes of motor duty we have covered in our lecture number 2, that short time duty, intermittent duty, continuous duty, all these things. Now another thing is that categorization of load variation. So we just uttered the sentence that different application has different parameters. Different application has different parameter or pattern. So we can categorize the load variation with time into certain categories, which are termed as that classes of duty of the motor. So according to the pattern, we decided the classes of duty of motor, and that we have discussed: intermittent duty, continuous duty, short time duty. Now a engineer who's responsible for the decide that for which application. Suppose in steel industry, an engineer is there, and it's has to implement in the slab billet boom in this rolling hot rolled mill section. So for that purpose, what should be the motor rating, that has to decide by that particular engineer. So one thing is that select a motor rating for a given application, ensuring that whatever motor I am selecting, for that application, it should not exceed that particular temperature limit, because then a thermal breakdown occur. So that is the prime work designated to a drive engineer. Now, so for that, we have just discussed that motor materials are heterogeneous, made of heterogeneous material. So different segments has different material, and so they have different heat conductivities. Okay, so for this thermal model development, we will assume that it is not made of heterogeneous material. Instead of, we will assume that it is made of homogeneous material, so that a simple thermal model of that particular machine can be obtained. If we consider the heterogeneous material made of, so it's not possible a standard thermal model. But in reality, all the machine parts are made of heterogeneous material. It is not made of homogeneous material. So whatever assumption I have made, it's inaccurate, but it's good enough for the determining the rating of the motor. Otherwise, it is not possible to decide the rating of the motor. Now how? Now let A assume that motor is made of homogeneous body and the cooling medium has the following parameter at time t. What is that parameter? P1, P2 is respectively heat developed and heat dissipated in watts. W is the weight of the active part of the motor. H is specific heat. A is the cooling surface area. D is coefficient of heat transfer, and theta is the mean temperature rise. Okay, we all know this from our basic physics concept in 11 or 12 in heat chapter. Okay, so we know all these things: specific heat, coefficient of heat temperature. We all know all these things. So if during a time increment, so time has incremented from T1 to T2, so T2 minus T1 is my dt, and temperature increase suppose from theta 1 to theta 2, so theta 2 minus theta 1 is my d theta. So a time increment dt, let the machine temperature rise, is d theta. Now we know from basic physical science concept of our class 9 and 10 that heat absorbed or stored in the motor is what? Is heat developed inside the motor minus heat dissipated to the surrounding medium. So it's very easy. We know all these things. We have read this in class 8, 9, all this here, or in these classes. Okay, so that is my heat absorbed. So how much heat is developed and how much heat is dissipated? If we subtract that developed heat from, if we subtract the dissipated heat from the developed heat, we will get the absorption. So what is my absorption of heat? Now the motor weight is W weight of the active part, and H is the specific heat, joules per kg per degree centigrade, and theta is the mean temperature, right? So it will be WH d theta. Theta is the mean temperature, right? Means, so H is specific heat per kg, for if the weight is W, so it will be WH into theta 2 minus theta 1, that is d theta. So WH d theta equals to heat developed inside the motor. P1 is my heat developed, so P1 in time dt, because time has in from T1 it elapses and goes to time T2, so P1 into T2 minus T1, that is P1 into dt. Similarly P2 into dt, and P2 is theta dA, heat dissipation. So what is this heat dissipation? heat dissipation is nothing but the mean temperature rise and the cooling surface area. So more the cooling surface area, the more the heat dissipation will take place. So theta into dA is my P2. The heat dissipation, P2 is my heat dissipation to cooling media. So it's my theta into dA. So if we substitute all this value, we will get C into d theta by dt equals to P1 minus d theta, and this is a first order differential equation. In place of WH, we put this C. C equals to WH, which is the thermal capacity of the motor. You should keep this C equals to WH, thermal capacity of the motor, because so many objective type question comes in GATE or any other competitive examination. So this is thermal capacity of the motor, WH. And D, what is my D? It is D into A, because theta is mean temperature rise, D is the coefficient of heat temperature per degree centigrade. So theta into D is we got, and it is per meter square. So we will multiply with A. So we will get joule per second. So that is my joule per second. Are you getting my point? P2 is heat dissipation into the cooling medium, joule per second, and D is the coefficient of heat transfer, joule per second per meter square per degree centigrade. Now what is my mean temperature rise? Is theta. So if we multiply theta with D, so it will become joule per second per meter square, and if we multiply it with A, with the cooling surface, it will become joule per second, which is my heat dissipated to the cooling medium, and that's why we have taken P2 equals to theta dA. And so this capital D is equal to D into A. This is heat dissipation constant. One is thermal capacity of the motor, another one is heat dissipation constant. Okay. Now heat dissipation mainly occurs through convection. We know heat can be transferred in three ways: radiation, conduction, convection. Okay, so here the heat dissipation mainly occurs through convection, and typical value of D. And what is my D? D is my coefficient of heat transfer, and it is typical value is from 60 to 600, or rather we can say in the range of 40 to 600 watt per meter square per degree centigrade. You look the unit, watt per meter square per degree centigrade. And this equation C d theta by dt equals to P1 minus d theta is my first order differential equation. So if we solve that differential equation, it will become, which we are not doing here, it will become, because time will not permit, otherwise I would have shown you how this solution is coming, but we have done in this in our mathematics, engineering mathematics in our 11 12. So I am not going to spend much time on this. So the solution will become theta equals to theta s plus k e to the power exponent of minus t by tau, and this k is obtained by substituting temperature rise at t equals to 0, and where theta is equals to P1 by D. What is my P1? P1 is my heat developed. What is my capital D? Capital D is my heat dissipation constant. Capital D is my heat dissipation constant. So theta is equals to P1 by D, and tau equals to C by D. What is C? C is thermal, and D is heat dissipation constant. So C is my thermal capacity, D is my heat dissipation constant. C thermal constant, heat dissipation constant. So this is give my tau, which is also known as thermal time constant. So thermal time constant is nothing but C by D. Now in this solution we have taken the initial value as 0. Now if initial value is temperature rise is theta 1, so the solution of the above equation is become theta equals to theta s 1 minus e to the power minus t by tau plus theta 1 e to the power minus t by tau. Okay. Now, if we put here at t equals to infinity, so if we put t equals to infinity, theta will become theta s, because this part is 0, this will become 0, so theta will become theta s. This theta s is the steady state temperature of the motor when it is continuously heated by a power P1. Now, at this temperature, all the heat produced in the motor is dissipated to the surrounding medium. Now, we have taken the temperature is rise from 0 to theta 1. So, I have previously I was taken the initial condition 0 and now temperature rise to theta 1. So, the equation theta equals to theta s plus k to the power minus t by tau will become theta equals to theta s 1 minus the solution. If we put the initial condition in a mathematics, so we'll it's mathematics, it's nothing is there. So, the equation will become this. And now suppose I have thrown off the load, I cut the load from my system. So now what will happen? Now the temperature will reaches the value theta 2, means there is heat loss, because now the load is not connected in the drive system. So the heat loss will reduce to a small value P1 dash. Previously it was P1. Now as the load thrown off, the heat loss component will reduce to a value P1 dash and the cooling operation of the motor start. Now if this heat loss component will reduce, so the heat dissipation constant will also change, D also change, because we have seen that D equals to D into A, D into A. So this, as this P1 is changing, so D is also change. So the new D is my heat dissipation constant in D dash. So the same equation which was previously was C d theta by dt equals to P1 minus d theta, it will become C d theta by dt equals to P1 dash minus d dash theta. So again, if we solve the equation, so we will know we have done this for theta 1, theta will become theta ss dash 1 minus e to the power minus t by tau plus theta 2 e to the power minus t by tau. Okay, so where theta ss dash is p1 dash by d dash and tau dash is c by d dash. Now this theta ss dash is again steady state temperature, right, for new condition operation. Previously it was heating, now it is cooling. So previously it was heating constant, now it is the cooling thermal time constant. Del dash is the cooling thermal time constant, and del was my heating thermal time constant. So one is heating time thermal time constant and another one is tau dash, that is cooling thermal time constant. Now if the motor were disconnected from the supply during the cooling, so now first the load has disconnected, now the motor itself disconnected from the supply. So if the motor is disconnected from the supply during cooling, what will happen? That if we put in this equation C d theta by dt equals to P1 dash minus d dash by theta, so this P1 dash will become theta ss dash, because d dash will become 1, this d dash will become 1, and both this P1 dash and theta 1 dash, this 2 will also become 0, because what is my P1 or P1 dash? This is my heat loss. So if motor is disconnected, so there is no heat loss. So if there is no heat loss, so there is P1 dash equals to 0. So P1 dash equals to theta ss dash equals to d dash, because you recall that d dash equals to d dash equals to d into a, d into a. this D equals to D into A, and D is my heating coefficient of heat transfer. So motor is disconnected, so there is no coefficient of heat transfer. So P1 dash equals to theta SS dash equals to, it will become 0. Okay, so this explains that the final temperature attained by the motor is the ambient temperature, and then the equation, if we solve that equation, this equation, it will become theta equals to theta 2 e to the power minus t by tau. Why? Because in this equation, this theta SS dash is becoming 0. So this term will become 0. So this term will left remain there. So theta equals to theta 2 e to the power minus t by tau. Okay. So this shows that both the heating time constant tau or cooling time constant tau dash depends on the respective heat dissipation constant d and d dash, which in turns depends on the velocity of the cooling air. Now in certain motor we used forced cooling. Okay, in self cool motor where cooling fan is mounted on the motor shaft, the velocity of the cooling air varied with motor speed. So if the speed increase, cooling air will also increase. So it will help in cooling much faster than if the motor run in slower speed, and thus varying the cooling time constant tau dash. And in medium and high power variable speed drive, what we used forced cooling, so that motor is cooling is independent of speed. So forced cooling method, it's independent of that motor fan. So this is the figure shows the variation of the motor temperature rise. So this is heating and this is cooling. Thermal time constant of a motor are far larger than electrical and mechanical time constant. So this is the main thing we should again remember, that thermal time constant of a motor is always far larger than electrical and mechanical time constant. Okay. So now I will solve one problem. Let me solve one problem. So this is my problem. A motor operates on a periodic duty cycle in which it is clutched to its load for a 10 minutes and then declutched to run on no load for 20 minutes, and the minimum temperature rise is 40 degree. Now what we know, my equation is theta equals to, just we have derived theta equals to theta SS into 1 minus e to the power minus t by tau plus theta 1 e to the power minus t by tau. Okay, now if we read this problem, if we see the motor is clutched for 10 minutes and then declutched for 20 minutes. So motor is clutched for 10 minutes, declutched for 20 minutes. So that means it is basically intermittent load type. We have studied what is intermittent type. So there is a constant load running period, then a rest period, then again a constant period running period. So the motor is subjected to a periodic intermittent load. So temperature at the end of cycle will be same at the beginning of the cycle. Both are same, because if we recall, for intermittent load the graph is like this. If you recall, the graph is like this. In lecture 2 we have covered this. So What? That means that temperature at the end of cycle will be the same at the beginning of the cycle. So it will rise, then it will reduce. So it is the beginning point, it is the end. So at the end of each cycle, it is same. Both these points are same value, in this same value. So now in this equation, theta equals to theta s is 1 minus e to the power minus t by tau plus 14 to the power minus 10 t by tau. So what I will do, I will now put the value. So it is theta ss value, steady state value is not given. So 1 minus e to the power minus, now for it is classed for 10 minutes, so it is 10. Now tau value, heating and cooling time constant both are 60, so I will put here 60. Now theta 1 is given, yes, that minimum temperature rise is 40 degree. So theta 1 is my 40, e to the power minus t is declass time is 20 minutes. No, so this is for maximum temperature is during duty cycle. So it will remain 10, that is clutch period. So 10 by again 60, because 60 is my heating time constant. So if we solve this, we will get 0.1535 theta ss plus 33.86. Okay, or from equation, that cooling period, that is theta equals to theta ss dash 1 minus e to the power minus t by tau dash plus theta 2 e to the power minus t by tau dash, where we will get from this equation theta is my 40. Okay, what is my theta ss dash? Theta ss dash is my declassed time. Is there anything given? Yes, when the load is declassed continuously, the temperature rise is 15. So this is my steady state temperature, so it will, I will put here 15. So now 1 minus e to the power minus t, declassed we are considering for cooling period, so it is declassed, so 20 divided by again 60 plus theta 2 is given. No, theta 2 is not given, so theta 2 e to the power minus 20 by 60. So from, if we solve this equation, so from here we will get the value of theta 2, because theta 2 is unknown, rest of the value is given. So theta 2 will become 49.9 degree. Okay, now what I will do, I will put the value of theta 2 in the equation. I will put the value of theta 2 in the equation, because here theta 2 equals to this. So if we put the value of theta 2 here, that is 49.9 degree. So we will get the value of theta s, and if we calculate, it will become 104.5 degree centigrade. Okay, now we will discuss, or we have discussed in our lecture number 2, the different classes of motor duty. We will just recapitulate that different duty cycle, and then we will move to the determination of motor rating for different duty loads, that is continuous duty, fluctuating duty, short time, and intermittent duty. Okay, so now classes of motor duty. So already we are discussed classes of motor duty in our lecture number 2, and I will cover this topic just for the recapitulation purpose. So we have seen in our lecture number 2 that motor duty can be classified into 8 basic categories. Okay, continuous duty, short time duty, intermittent duty is the 3 duty which is known as the basic duty. Okay, now in continuous duty, if you see that the motor operate in constant load and it operate for a long time, and this time is enough to reach the motor in steady state condition. Okay, and the example is paper mill, compressor, fans, etc. Now short time duty. So this is the short time duty. Now in short time duty, the operation time of drive is less than the heating time constant. So for short time duty, operation time is less than operation time is less than heating time constant. So if it is less than heating time constant, so what will happen? So it goes, it will rise this temperature and then it will goes to ambient temperature. It will reach to the ambient temperature. That is the, it will totally cool off, allowed to cool off to ambient temperature before motor is required to operate again. Okay, and in this operation the machine can be overloaded until temperature at the end of loading time reaches the permissible limit. If it is crossed the permissible limit, then only it is overloaded. Means up to the permissible limit it is allowed to be overloaded. That is the meaning. The machine can be overloaded until temperature at the end of loading time reaches the permissible limit. So these are cranes, valves, drives for position control. Now the third one is intermittent periodic duty. So this is consist of duty cycles. Okay, so it is basically running for a constant load for certain time, then there is a rest period and it is repeating in this fashion. So there is a constant load and a rest period. Now one thing, neither this running period is enough or sufficient to rise the temperature to steady state value, nor this rest period is long enough for the machine to cool off to ambient temperature. What we have seen in case of short time duty. Short time duty, it is cool off to the ambient temperature, but in case of intermittent duty, not the running period, neither the running period nor the rest period is enough to either to rise the temperature to steady state or to machine to cool off in ambient temperature. So the example of this is metal cutting, drilling tool drives, forklift drives, etc. Now when we have talking about intermittent periodic duty, we have neglect the heating effect of the machine during starting and braking operation. Means heating of machine during starting and braking operation is negligible. We have neglected this. Okay, so continuous, short time, intermittent periodic duty, it has covered. Okay, now the fourth one is intermittent periodic duty with starting. So that also we have discussed, that in case of intermittent periodic duty with starting, in this we cannot neglect the heating or heat loss during the starting period. We cannot neglect the heat loss during starting. And when we have discussed intermittent load, we have discussed that starting and in starting and braking condition we have neglected the heat loss, but in certain duty we cannot neglect the heat loss due to starting. We cannot ignore that. So what will happen? It has a period of starting, consists of a period of starting, a period of operation at a constant load, and then a rest period. Okay, so what will be the curve? So the curve is curve is, so there is a starting period, then a constant load running period, okay, then a rest period, and it will repeat in this fashion, okay, and it will repeat in this fashion. Sorry. So again there is a starting and then again running and then again 0 and so on. So this is my starting period, this is my running, and this is my rest period, okay. So what we can say here, that in this condition, that is the intermittent period duty with starting, with operating and rest period, this is my operational period, this is my operational period, and this is my rest period. So both these operational period and rest period are too short for respectively steady state condition cannot be reached in this condition. So its curve will be, so it's so this is torque versus time, this is duty cycle versus time. So the curve will be, so it will reach to a value again this way, again it will try to reach the ambient, but it will not enough time, so again it will repeat, okay. So in this fashion it will go. So example of this is metal cutting and drilling tool drive. Drive for fork lift truck. Drive for forklift trucks. Drive for forklift trucks, okay. Now in this duty, that is the intermittent period duty with starting, we should keep in mind that in this duty, heating of machine during braking is considered negligible. During the braking period, heating is considered to be 0 because mechanical brakes used for stopping of the motor, and the another way, due to its own friction, motor will stop, okay. Now intermittent periodic duty with starting and braking, this is with starting. Now with both starting and braking, so now intermittent periodic duty with starting and braking. Now I will consider this, both these two, starting and braking, which we have not considered. The braking I have not considered in the previous duty, we have not considered. So in this what should be the curve, torque versus time curve? What should be the torque versus time curve? Now there is a starting torque, okay, and there is a constant running torque, then there is a braking torque, okay, then there is a rest period, and the circle will repeat, okay. So there is a starting torque, so there is a starting period. Now there is a period of operation with constant load, so this is running with constant load, and then this is braking time, braking period with electrical braking, and this is my rest period. Okay, but here the operating and rest period. So here also the operating, this is operating period and this is my rest period. Both are again too short for respective steady state temperature to be attained. The example of this billet mill drive, the example of this billet mill drive, manipulator drive, manipulator drive, ingot Bragi drive. So these are few examples. Okay, so these are the examples. And also drives for electric suburban trains, also drive for electrical suburban trains. So this is the most important example of intermittent duty with braking and starting. Drives for electrical suburban train. Now if you see in electrical suburban train, there is a starting period, then there is a running at constant load, and then when the station will reach, before 2 minutes it will put its brake, so there is a braking period, then again there is a rest period, and then it again start running for the journey to the next station. So it is the most important example of intermittent periodic duty with starting and braking. So these are all basics classifications of duty. So the three other duty left, that is if there is no rest period. So we see in intermittent duty there is rest period. So if there is no rest period, so it will be a continuous duty. Okay, so if there is no rest period, it is a continuous duty. So it is a continuous duty. Now this continuous duty classified into continuous duty with intermittent periodic loading, with intermittent periodic loading, continuous duty with starting and braking, continuous duty with starting and braking, and then continuous duty with periodic speed changes, with periodic speed changes. So this intermittent periodic loading, starting, braking, and periodic speed changes. Now intermittent periodic loading is that it is similar to the intermittent periodic duty with starting. Okay, only difference is that in case of intermittent periodic duty there is a rest period, but here there is no rest period. Okay, unless in spite of that rest period there is a period of running at no load. So instead of rest period, there is a period of running at no load. No load. There is a period of running at no load. That means its duty cycle is consist of a period of running at a constant load, a period of running at no load with normal voltage. Again it will repeat. That is again the load period and no load period repeat. And this both period, load period and no load period, both are too short for respective temperature, steady state temperature to be attained. Okay, so the distinguished with the intermittent periodicity is that the period of running at a constant load is followed by a period of running at no load at instead of rest. So if we draw the torque versus time curve, So it will be like there is a constant running period, okay, and there is a no load period, and then again it will repeat in this fashion, okay. So the example of this: pressing, cutting, shearing and drilling machine. So pressing, cutting, shearing machines. These are the few example, okay. These are the few example of continuous duty with intermittent loading. Now continuous duty with starting and breaking. So what will happen? This again consists of a periodic duty cycle, each having a period of starting, a period of running at a constant load, and then a period of electrical breaking, but there is no rest period. So what will be the curve? 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 The curve will like this. Sorry. So torque versus time. So what will be? There is a starting period. So there is a starting torque. Now there is a running torque. Now there is a braking torque and no rest period. So again the starting torque and then running torque and so on. So there is a starting period, there is a running period, there is a braking period, but there is no rest period is there. That's why continuous duty with starting and braking. A blooming mill is an example. So the example of this continuous duty with starting braking is drive for blooming mills. Now periodic continuous duty with speed change. So as the name suggests, that is consists of a periodic duty cycle, each having a period of running at one load and speed, and that and another period of running at different speed and load. So one at suppose omega m1 speed and load torque T1, then again omega m2 speed and torque T2. So it will in this way go on. So one for omega 1 T1, then another one for omega m2 T2 and so on. So this is my continuous duty with periodic changes. So this is all about classifications of duty. So in our next class, I will start determination of motor rating for continuous duty, fluctuating loads, short time and intermittent duty, and then we will calculate equivalent current, torque and power method for fluctuating and intermittent loads. Okay, so this will be my aim for next class. So we are come to the end of today's class. So these are my references which have been used, and thank you.